two. Let's just make sure that people on Zoom can hear us well.
Oh, yeah.
So on Zoom, are you able to hear us in the room?
Yes, we will.
Excellent, and we can hear you very clearly, so all is going according to plan. We do have a small group of maybe 12 people in the room here. The labs were running, people were here for their research, and so those of us who are running the campus just gathered here for the talk. And I'm going to, you get me, the weather. I'm going to introduce Laura. I have the pleasure. Laura got her PhD at Columbia in 2018 for building, characterizing, deploying, analyzing data from quiet, which is an interesting acronym for an experiment. She did her postdoc at Princeton and has been at Yale working on an array of experiments that people are familiar with, CHIME, HIRAX, the Simons Observatory, and a lot of work to make the next generation of positive microwave background experiments possible. I think you're largely known for data acquisition, data analysis in general. Around here, we think of Laura as the person with the coolest undergraduate research projects and graduate research projects, building and flying drones over experiments to do calibration runs, which, I mean, it's hard to compete. I've tried to compete with Laura to get a student, and I have to say that that's really difficult. So today we're going to hear new results from the CHIME experiment, and I have to say, Laura, I remember the first time I heard you talk about CHIME. I still remember that very first talk. I couldn't believe how creative it was that people had realized, you know what, we don't have to go for the greatest resolution here. We actually have a scalable experiment that's buildable, that's going to teach us something really interesting and important about the universe that other people can't get to. So, thrilled to hear what the latest and greatest is from CHIME.
Thank you, Sarah, for that awesome introduction. And I can skip all of my CHIME introduction. She did a great job giving you the basics of why CHIME, why we built CHIME. And thanks to everyone who's here. Thanks to everyone online who took a break from shoveling their cars out or watching their kids to hear about CHIME. So today I'll be talking about new results from the CHIME experiment. CHIME is the Canadian Hydrogen Intensity Mapping Experiment. It's a radio interferometer we built in Canada that started taking data back in 2017. So we'll be talking about new results that are hot off the presses on the archive at the very end of last year. Okay, so my fellow CHIME collaborator, Tom Landecker, once told me that there is nothing new in radio astronomy. So I'm hoping today I can prove that that is both true and false at the same time. All right, so as a cosmologist, of course, I start out with lambda CDM. This is our standard model of cosmology, at least circa a few years ago. So the lambda in lambda CDM, of course, is standing in for dark energy here. So this is, if you think that dark energy is associated with a cosmological constant, we denote that with a lambda. So lambda here is dark energy and CDM is cold dark matter. Together, this makes up about 95% of the total energy content in the universe. So lambda CDM is our standard model of cosmology. It describes the past 14 billion years of cosmic history really pretty well. So we know the universe started off with a big bang about 14 billion years ago. We believe it proceeded through a period of rapid expansion, inflating over 25 orders of magnitude in the space of less than a second, when the universe was less than a second old. From there, the universe continued to expand and cooled as it expanded. After a few minutes after the Big Bang, the first nuclei formed in Big Bang nucleosynthesis. Afterwards, the universe continued to cool down. Eventually, neutral hydrogen could form, and it so happened that released the cosmic microwave background, which, of course, we measure today. And from that primordial neutral hydrogen, the first stars and galaxies formed. A few billion years after that, the expansion rate of the universe began to pick up. This is what we attribute to dark energy. And then fast forward all the way to today when we get to look back at all this glorious cosmic history with our telescopes and learn all about it. So our lambda CDM model has done a really excellent job telling us how all of these different components came to form as a function of time. I was reminded of an excellent example about how well we understand the universe in our recent Gruber Symposium this past fall. So the recipients of the Gruber Prize had measured the amount of deuterium in the early universe and measured it to be, don't worry about the number, but they measured it to be this gray band. The cosmic microwave background, so that's the y-axis here, the cosmic microwave background can be used to tell us how many, the amount of baryons in the universe, that's this purple band here. And the theory curves from Big Bang nucleosynthesis models are these green curves. So you can see everything intersects right in the same region to basically better than 1%. So this is one of the examples of how excellent lambda CDM is at describing many different observables in our universe. Of course, recently we've had some troubles in lambda land. So a few years ago now, and as Nikhil talked about in his physics club last year, measurements from DESI, a galaxy survey, began to find some tension with lambda, the cosmological constant. So I'm going to walk through that for a second. So on the x-axis here is W naught. This is basically how dark energy depends on volume. So as the universe expands, how does the quantity of dark energy change? And WA is the time dependence of that number, so how this changes over time. If lambda, if a dark energy is a cosmological constant, you would expect it to be right at the intersection of these two curves. So it has a value of -1 on the x-axis and no time dependence at all appear on the y-axis. The measurements from DESI are in varying degrees of tension with that cosmological constant model. So these are the DESI curves. The different colors just denote different combinations of data, but all of them are predicting something different from or finding something different from lambda. So we've begun to think a little bit beyond what a cosmological constant, beyond a cosmological constant model for dark energy. So I decided to draw an analogy with dark matter. So for those of you who have not had the pleasure of being part of a snowmass process in the last few years, this is a schematic by Tim Tate. This was all the way back in 2013, showing many different models that could describe dark matter, their various interactions, and how they can, how they overlap with each other, and showing just the enormous theory space that exists in dark matter. I decided to try my hand at drawing the dark energy version of this. You should not take this terribly seriously, but this is just to say the theory space for dark energy is broad. People have been thinking beyond lambda for a very long time now, at least the past 20 years since we've known about dark energy. And so there are various different models relying on scalar fields, vector fields, et cetera. I don't know if Sean knew this, but there was even a paper where time crystals could be dark energy. So varying degrees of different models trying to describe dark energy beyond just a cosmological constant. So of course, we'd like to understand which of these models could be in play. If so, what parameters we should use for them, and take advantage of this enormous theory space to really begin understanding what dark energy might be, whether it's lambda or not. So to do that from an experimentalist perspective, we need more data. So what would we like to do to understand what models of dark energy might be in play? What we'd really like is to measure the entire expansion history of the universe. So really go back to when dark energy began impacting that expansion rate and measure the history of the expansion. So we measure it as a function of time to nail down how the expansion rate is evolving with time, and then identify which models are compatible with that. So how do we do that? How do we get a measurement that actually tells us how the universe, how that expansion changes with time? Well, the universe has given us an interesting signal, so I'll first describe it. So if we look back when the universe was about 300,000 years old, And we make a measurement of the cosmic microwave background generated when the universe was 300,000 years old. If we take all the hot spots in the cosmic microwave background map and stack them on top of each other, or cold spots, we find a ring-like feature present in that data set. If you did the same thing with galaxies, you took a map of all the galaxies in the universe and you stacked them on top of each other, you would also find, this is an artist depiction, this is real data, this is an artist depiction, you would also find evidence for a ring-like feature left over in the galaxy distribution. And these come from the same fundamental scale. So the non-cosmologist in the audience might be wondering, how do I get a signal that is common both from the universe when it was 300,000 years old and billions of years later in the distribution of galaxies in the sky? How did that work? So we're going to trace, so this is easy to understand. We have to cast our minds all the way back to the beginning of the universe. When the universe was less than 300,000 years old, it was very hot and very dense. Photons and baryons were coupled together. So the fluid itself was coupled. Throughout the universe, there were small overdensities seeded from the beginning of the universe. And everywhere there's an overdensity, we end up with a small pressure wave that will propagate outwards from this small overdensity. So it creates an overpressure spot that relieves its pressure by propagating away through the fluid. Because photons and baryons are coupled together, both the photons and the baryons will propagate in this pressure wave. So we're going to watch a pressure wave propagate outwards from one of these overdensities. So here we have an overdensity. The pressure wave is moving away from it in a ring-like feature. Of course, we don't have only one overdensity, we have many of them. So a pressure wave is going to propagate outwards from each of these overdensities. Again, both the photons and the baryons are propagating away in these ring-like features. This happens until the universe is about 300,000 years old. At that point, the photons and the baryons dissociate from each other because neutral hydrogen forms. That reduces the scattering that was keeping those photons and baryons coupled together. Sorry, the video got away from me. So you should imagine that the CMB, when the CMB was formed, those pressure waves stalled and the baryons got left behind. So we'll see the photons again as the cosmic microwave background, but the baryons ended up in the central overdense region and then in ring-like patterns from those pressure waves propagating out from the overdense regions. Anywhere there's an excess of baryons, you're going to end up with more galaxies. So we end up preferentially building galaxies in these central overdensities and then in these ring-like features outside of them. So we end up with an overall bunch of ring-like features in the distribution of galaxies in the sky. So this is something we can measure, and in fact, DESI and many other galaxy surveys have measured it. DESI is the most recent one. So if you made a map of all of these galaxies and asked how far apart are each of these galaxies in the sky and built up a histogram, you would get something like this. So this is distance between galaxies, and this is more or less how many is the histogram, so it's more or less how many of those distances are we finding. And we find there's a particular scale left over in the distances between galaxies. This is exactly that remnant ring-like feature. So now we have a measurement of this ring scale left over in the distribution of galaxies in the sky. So this is exactly what we want to understand dark energy better. We have a scale that was set in the cosmic microwave background, so we get to measure it in the CMB very well. And then we get measurements of that scale in the distribution of galaxies at different redshifts. So this ring-like feature expands as the universe expands. So if I measure a bunch of galaxies at one slice, at one redshift or one time in the universe, then I measure other galaxies at a different redshift or a different time in the universe, I can see how that scale has changed with time. So this gives me a sensitive measurement of expansion rate with time, which is exactly what I want to understand the effect of dark energy and the models that will ultimately describe this. Good. So what I want to build is a galaxy survey that measures every galaxy very well at many different redshifts and also knows exactly when those galaxies were formed. So exactly what redshift I'm measuring those galaxies at. So to understand how to do this, we should understand first how DESI did it, because they did exactly this measurement. So what did they do? So if I build a simulation of the universe and I run it forward and I say, where do I develop galaxies? I might get a picture like this slice. So everywhere there's a gray dot, I managed to form a galaxy in this simulation. What DESI does is say, okay, I'm going to take a picture of the sky and identify which galaxies I can find with my very fancy spectroscopic instrument, which will tell me the redshifts of those galaxies very well. And the galaxies that DESI may be able to target are shown in red. So there are these sparse red dots where DESI has decided this is a galaxy that's suitable for targeting with our instrument. So you can see there are many galaxies that DESI could not select because they're too dim or it didn't seem right for one way or another. Shown for scale is this BAO feature size, this ring-like feature size that's going to tell us about dark energy. So you can see this ring-like feature size is much bigger than any individual galaxy. I have to measure many galaxies to be able to pick it out. So we would like a way to measure all the galaxies instead of a sparser, less statistically complete sample as shown by the red dots. So let's open our minds up for a second and imagine that we could just measure the average emission from all the galaxies together. So if I made a blurry map where I measured the average emission from all of these different galaxies with a really blurry telescope, so I didn't go and find individual galaxies, but I did somehow manage to measure the intensity from all of them, I could still pick out this overall feature size that's going to tell me about dark energy, but I didn't have to go select individual galaxies. I could just make an integrated map of all of the emission. So I don't really need DESI. What I do need is something that will measure the average emission or the aggregate emission from all of these galaxies and have redshift information. So I know exactly when in time these galaxies emitted their light. So luckily, nature has given us exactly a way to do that. So all of these galaxies are bright in neutral hydrogen. So neutral hydrogen has a very special transition. When the electron goes from spin-aligned to spin anti-aligned, it emits a 21 centimeter photon that we get to measure with our radio telescopes. So we could make a measurement of all of these gray dots in 21 centimeter radio emission instead of going back and trying to follow them up with an optical telescope. That 21 centimeter emission gives me the redshift, and the average emission from our blurry map will allow me to still pick out this BAO feature size. So of course I'm not going to make a telescope that's sensitive to 21 centimeter light. I'm going to make a telescope that's sensitive to redshifted 21 centimeter light. So for example, if I was interested in a map at a redshift of 0.8 when the universe was about 7 billion years old, I would make a map at about 37 centimeters, and that's because the 21 centimeter light has now been redshifted to be a longer wavelength. So I'd make a map at about 37 centimeters. Similarly, if I was interested in, say, a bunch of galaxies that are a redshift of 2.5, when the universe is about 3 billion years old, I would make a map at 75 centimeters because, again, that 21 centimeter light has been redshifted to a much longer wavelength. So if I were interested in galaxies between redshift of 0.8 and 2.5, I would build an instrument sensitive to 37 to 75 centimeter photons or 800 to 400 megahertz. So my frequency, my radio frequency, is an exact map to the redshift. And I can easily make blurry maps of the sky with radio telescopes. We do that all the time. So we built a telescope to do exactly that. This is the Canadian Hydrogen Intensity Mapping Experiment. It operates between 400 and 800 megahertz. So that's that 0.8 to 2.5 redshift range. That's when dark energy began impacting the expansion of the universe. So this is a good target for understanding dark energy better. The telescope itself is a set of 4 cylinders. Each of them is 20 meters wide by 100 meters long. So we have 100 by 80 meters of telescope on the ground. Our resolution as a result is about 1/4 to 1/2 of a degree. So picture something that's the size of the moon or a little bit smaller. So a very, very blurry map of the sky. We have 1,000 frequency channels. That's equivalent to 1,000 redshift bins. So we make a spectroscopic map of the universe with our radio telescope. The signal itself is very dim, so we need to make a sensitive measurement. So as a result, we have 1,000 detectors basically on our telescope. And as I'll discuss in a second, this unique design for the CHIME reflectors maps half of the sky every single day. So we make a map of the entire sky every day, or the entire sky visible from Penticton, where CHIME is located every day. So this is going to come up a few times, so I just want to describe how CHIME actually sees the sky with our cylindrical reflector. So let's start with a simpler example. If I just take a single detector, a single radio feed, and put it on one of our cylinders, the shape of the beam on the sky, the sensitivity of my instrument on the sky, is an enormous hot dog. So it's 2 degrees, so in the focus direction, in the direction where we can focus the light, it will be about 2 degrees wide. But there is no focusing power along the cylinder. So we have sensitivity to the entire sky in the north-south direction, and it's shaped to be about 2 degrees wide in the east-west direction. Okay, that seems like a really tough and useless telescope, and you'd be right. So we don't do that. Of course, the next thing we do is put a bunch of detectors along the focus of our cylinder, and then we correlate the signals together. So every single feed goes into our instrument correlator, and we correlate pairs of feeds together. This is radio interferometry. So this allows us to be sensitive to scales inside of our telescope. So for example, we end up with higher resolution in mini beams with higher resolution inside of our big long hot dog shape. And that's because when we correlate the signals together, we end up with sensitivity to scales corresponding to the baseline between the feeds. So the baseline is just the distance between the feeds. The longer my baseline, the higher the resolution of the correlated data set. And so I end up being able to form smaller beams inside of my hot dog with higher resolution. So I can measure smaller scales in my map than just this hot dog shape. So that's good. Of course, I can play that game. I have 4 cylinders, so I can also correlate the signals between cylinders, and again, populate in my east-west direction, populate a bunch of mini beams inside of this big long hot dog. So this gives us higher resolution than just that hot dog shape on the sky. And now, as the sky rotates from east to west, I just map out the sky with each of my little mini beams inside of this hot dog. So this is a map from CHIME at 679 megahertz. So this is east to west. So the sky rotates east to west, and we just fill out this map as it rotates through. CHIME itself doesn't move. We rely entirely on the sky rotating to be able to fill this map out. I'm going to first point out the brightest thing in this map, which is our galactic plane. So this big bright thing that swoops down and comes back up in this projection is the plane of our own Milky Way galaxy. It is incredibly bright. What you may notice from this map is it does not look like a bunch of tiny little extragalactic galaxies the way that, say, a DESI map does. Instead, it looks mainly like emission from our Milky Way galaxy. That is true, and that is one of our biggest challenges for CHIME. So if we compare our actual CHIME map, the brightest thing, or the average emission, is about 10 Kelvin on our CHIME map. We can simulate what we think the 21 centimeter signal brightness should be, and it's about 10 to the minus 4 Kelvin. So there is a 5 to 6 order of magnitude difference between the signal that we want to measure, that's going to tell us about dark energy, and the brightness from foreground synchrotron emission from our own galaxy and extragalactic galaxies. So this is bad. I will admit that we knew about this problem before we built CHIME. So we did actually know that the galaxy existed before we built CHIME. So why did we think that this was possible? So we're taking advantage of the fact that synchrotron emission is smooth as a function of frequency. So if I measure synchrotron emission at one particular frequency in my 400 megahertz wide CHIME band, I can pretty much predict exactly what it's going to be at all of these other frequencies. So that synchrotron emission is incredibly smooth with frequency. Conversely, our 21 centimeter signal is not. That's because what we're measuring is a lot of galaxies at one redshift, so one frequency here on this axis, and at another frequency, it's a whole bunch of other galaxies that are totally not correlated with the galaxies at the other frequency. So it's just basically a Gaussian random distribution along frequency for the 21 centimeter signal. So the experimentalists in the audience and the theorists in the audience know exactly what to do with this. You say, I'm going to high pass filter. I'm going to just keep anything that evolves quickly with frequency, and I'm going to kill anything that's smooth in frequency. That will remove all of my foregrounds down to 0 Kelvin, and I'll be able to keep just my 21 centimeter signal that I'm so interested in. So, so this is more or less our plan all along for CHIME. Good. So we're just going to high pass filter our data. We make measurements at 1,000 frequency bins. We high pass filter it and keep whatever's left, and we're sure that will be 21 centimeter signal. So this is our map from our most recent results. So this is, digits are over there. So this is about the same frequency, 678 megahertz. This map does not look like this map. There are a few reasons for that. I'm going to walk through them in a second. The first and most obvious one is we selected a little tiny chunk of the sky, not tiny, a large chunk of the sky away from the galaxy. So we got rid of some of our problems by just not worrying about the actual plane of the galaxy. We're going to pick a region that at least looks cleaner visibly. We then removed what we call short baselines. So again, I'll go back and discuss this baseline geometry for CHIME. Long baselines have sensitivity to the smallest feature sizes on the sky. It's like building a large telescope. So you may recall that the resolution of a telescope goes as 1/d. So the bigger your diameter of your telescope, the finer the resolution you can measure. Conversely, short baselines, closely spaced baselines, are similar to building just a tiny little dish, like a 3-meter dish you'd stick outside for a random radio lab. So those short baselines have sensitivity to the big, fuzzy, diffuse stuff, the unresolved, diffuse stuff in the galaxy. So this allows us to kill a lot of the structure in our own galaxy just by choosing which exact pairs of feeds are going to go in our sum. And then finally, we do this high-pass filter. In CHIME lingo, it's called a delay filter. So this removes all that common structure that's common along frequencies, the kind of common mode along frequencies. So we've done many other things to our data to get to this beautiful map, but it looks like noise, which in cosmology is exactly what we want. And the main visible things that we've done to make it look different from this map are these three things. So now we're going to take this map and we're going to run it through our cosmology pipeline. So cosmologists are not interested in maps. We don't really like maps very much. We like power spectra much more. That's because we're always looking for these fluctuations in the sky. So we're looking for BAO feature sizes or its harmonics. And so we don't really know what to do with maps. We immediately turn these into Fourier transforms. So CHIME makes these beautiful, clean, noisy-looking maps at 1,000 frequencies. For the analysis that I'm describing here, we took just 100 megahertz of that band. So from 600 to 700 megahertz, that's about 200 maps. And we're going to Fourier transform this to turn this into modes because we think about fluctuations more than we think about maps and things in the sky. So we get 3 dimensions for a Fourier transform. 2 of them are spatial, and 1 of them is along the frequency or the line of sight direction, so looking backwards in time. And then to boost our signal to noise for this paper, we combined, we summed the 3-dimensional Fourier transform down into a 1D. So we just collapsed the 3-dimensional Fourier transform down into 1D to just boost our signal to noise to fluctuations. So this is our result. So this is our power spectrum of 21 centimeter fluctuations. I'll walk you through it for a second. So the x-axis here is mode. So again, this is just Fourier transform mode. That means smaller scales are over here, larger scales are on this side. The data itself is a correlation between even and odd days to remove our noise bias for the experts in the audience. So the data set itself should just be real, like literally real, and is indicated by these red lines. So our power spectrum are these red points, and a model fit to these data points is shown as the black line. So I'll talk about a couple of things. First is this is a 12.5 sigma detection of the 21 centimeter power spectrum with CHIME only data. The model that we're fitting is basically an amplitude, so an overall scaling times a matter power spectrum with some nonlinear degrees of freedom in there, and is a nice fit to the data. You can see the residuals down in this lower panel. Good. And so that I don't forget to say this, this is the highest redshift 21 centimeter power spectrum measurements made ever, and also the highest redshift one without using any external data. And so the previous competitors for this award is CHIME itself, where we used external data to get a high signal to noise by stacking on galaxy catalogs. So this measurement, the one that I just showed, is the highest redshift. It's equivalent to a redshift 1, highest redshift 21 centimeter power spectrum made to date by any group or any telescope. I'll stop here and just say that's a huge benchmark for the field. So people have been trying to make 21 centimeter measurements for over 15 years now. So to be able to do this with CHIME only data without reference to any external galaxy or any external catalogs is a huge milestone for pushing this field of making measurements from radio telescopes possible. So this is a high watermark for now for the field. All right, so from here, I could go and discuss this model that we fit. I could talk about the posteriors. I could mention all of the jackknife tests that we did. So I could go on and on about the results in our 50-page paper. If you wanted that talk, I'm sorry, that's not the one I'm giving you. So instead, I'm just going to cut to the chase and say none of the parameters that we're going to constrain with this power spectrum involve dark energy. So if I look back at our really nice results, this gorgeous 12.5 sigma result with its fit, if I compare it to the feature size that I'm interested in, that's going to tell me about dark energy, that lives down here. So this lives at larger scales, both on the sky, but in particularly a long frequency, than we presented in this data set. CHIME itself was built to have access to these scales, so this problem, yeah. Yeah, good question. So we have a lot of radio frequency interference, so cell phone, et cetera, digital cable, cell phone towers, things like that. For this particular analysis, we wanted to select the largest chunk of clean frequency bands so that we didn't have to work too hard to filter out our data to handle the places where we had to remove the data. So this is not a fundamental limitation, it's a choice for being able to move forward with some kind of detection. Yeah.
So how the error bars and segmentation of the presentation, so how do you determine the error bars?
Yeah, how do we get the error bars here? Yeah, so this came from taking even and odd differences between our data sets. So we have, I should have said, this is 94 nights of data, which is also much less than our total data volume. We've been taking data since 2017. So it's a tiny fraction of our overall data. These error bars were assessed by taking differences between those even and odd data sets, and then the residuals from those even and odd data sets were formed fundamentally these error bars.
Okay.
Yeah. Yeah. Oops, that was not. so the signal of interest is going to tell us about dark energy lives at larger scales, larger modes than we presented in this analysis. So why did we do that? Or conversely, what is our path forward for getting back these scales? So I'm going to now draw your eye to the features in the map that I didn't discuss before. So again, this is the galactic plane, and I spent a lot of time talking about how it's about 10 Kelvin. I didn't talk about these features in the map. So this is a point source as it's transiting through CHIME's beam. This is more or less where it's transiting, and then this is sensitivity to that point source far off into the distant side lobes. So when the source itself is many, many degrees away from where the telescope itself is looking, we still have a lot of sensitivity to it. This is our instrumental beam on the sky. It is both annoying because it goes pretty far away from our transit direction and also is highly frequency dependent. So the particular locations and brightnesses of all of these different spots on the sky change as a function of frequency. Fundamentally, that's one of our biggest problems for CHIME. So the thing that does is take our nice, beautiful, smooth foreground. So again, this was how we were going to handle foregrounds. We were going to take our smooth thing, and then we were going to high-pass filter it. If I have a frequency dependence in my instrument that I have not accounted for example, that beam shape, I multiply that foreground by anything about my instrument I didn't calibrate away. So I end up with, ripple-y type structures multiplied by this huge bright foreground signal. So now when I do that high-pass filtering, I'm still left with a lot of residual frequency-dependent structure that simply comes from not having calibrated and removed my instrument from my data set. And this means fundamentally we have to filter more strongly in our frequency direction than we would like. That's what removes our sensitivity to those baryon acoustic oscillation feature sizes. So obviously this means we need to measure the beam of CHIME. How do we do that? So the first question is, can we do this from CHIME data itself? Can we just use this map? Here we made a map. Here's a point source as it goes through CHIME's beam. Can we just use that? And the answer, unfortunately, is no. CHIME itself has good sensitivity and can measure all this point source out very far in its own data when it's combined all of its detectors together. So once we've co-added all of our data together, then we can see this point source. In any individual pair of feeds, we do not have the sensitivity to point sources to see that. That's because every pair of feeds is still fundamentally measuring the point source and the entire sky behind it. And so the sensitivity to a given bright point source is not very good. So in a single pair of feeds or a single data chunk from CHIME, we do not actually have access to this signal as it goes away from the main beam. So we can't use CHIME's data itself to calibrate its own beam. So what do we use? So one of the things that we're using is holography. So this is a measurement that I developed when I was a postdoc and have been doing while I've as a faculty here. So we have a nearby steerable dish right next to CHIME. We instrumented it with a 400 to 800 megahertz speed. The signal from this telescope goes all the way through a bunch of coaxial cables and amplifiers and ends up in the CHIME correlator. So we're able to correlate the signals between this dish and all of the individual detectors on CHIME. What does that do for us? We are allowed to steer this dish. It's a steerable dish, so we can track point sources as they transit through the CHIME beam. That evades this problem where in a given pair of feeds, we don't have sensitivity to a point source and allows us to zoom in on the signal just from that point source. So this is a paper written by my graduate student, Alex, showing measurements from this holographic technique. So this is, I'm gonna walk through this a little bit. So this is angle across CHIME, 0 means transit. The beam shape from CHIME has a kind of Gaussian main beam, so this is what you would normally expect from a regular telescope pointed up, and then has all of this additional side lobe structure away from the location where we're pointing. So that's similar to what I showed in that map. There are actual error bars on this measurement that are statistical. It's hard to see. There are maybe a few places where you can see some brown fuzz, but these are but it's hard to see the error bars because these are incredibly precise measurements of the beam. We can identify differences between the different cylinders. So this is a coad of all of the feeds on each cylinder, and there are small shifts in the pointing and beam shapes even from cylinder to cylinder. We also have access to a cross-pole signal. So this is not something I talked about before, so I'm going to mention it now. The antennas that are on CHIME are dual polarization. So we have one polarization that is aligned orthogonal to the long direction of the cylinder, and one polarization aligned on the 20-meter direction. The feed that's on top of the 26-meter is also polarized, so we can measure both the polarization that's aligned with CHIME and also any interfering cross-pole, so any signals that are coming generated in one polarization and picked up in the orthogonal polarization. So that's this cross-pole signal, which you can see relative to the main beam. And we also measure that quite well. It also has lots of fun structure in it as well. I'll highlight this. The typical cross-pole feature is a kind of double bump. So there's a bump on each side and then a minimum right at the transit. That's a classic cross-pole pattern. So this data was used already. The main beam, so that Gaussian shape, has been used in all previous CHIME results. So those are the results I just showed, and then also a previous publication. It was also used to estimate the brightness of a fast radio burst and associate it with a galactic magnetar. More people are using it for other fast radio burst and pulsar measurements. So these holography data sets have been used both in the CHIME cosmology collaboration, but also for the transient pipelines as well to estimate the brightness of their transient sources. So this is Alex, the author of that paper, talking about it in an interview with the AAS editor. So this is just for the experimentalists in the audience. I wanted to do a brief aside. There are many great things in that holography paper. This was one of the more fun ones to come together. So this is a measurement of tau A. It's at a location where you can actually measure CHIME's beams with the sun. So there's a solar data set here shown in black, and then the holography data set shown in blue. We can measure both polarizations, X and Y. And we see that the two measurements largely agree in this first upper polarization, this YY, but are incredibly discrepant down here for the other polarization. In particular, the solar data is finding this funny double bump feature with a minimum in the center and does not at all match the holography data. So this is not true everywhere in our beam. It's true at some frequencies, at particular locations in the beam, and only for this one polarization. We can resolve this discrepancy using holography data if we add the cross-pole data from holography. So if we add the full polarization information, we can recover what the solar data is finding. What this is actually evidence for is significant polarization leakage in CHIME's beam shape. So because it requires a large degree of that cross-pole signal, we're finding a polarization systematic in CHIME's beam. This was not findable any other way. This really required holography to be able to identify the difference between the two different polarizations, co and cross-pole. All right. So I wanted to end on more futuristic ways of mapping beam shapes. So we have begun a program of using drones to map beam shapes for these radio telescopes. So this is an example from a paper that two of my graduate students wrote. We went to Green Bank and measured 4 different telescopes that happened to be operating in the CHIME band. So the concept is pretty straightforward. We take a transmitter, basically we build a radio transmitter, put it on a drone and fly it over the telescope. So we're just flashing a big, bright radio signal as we fly in a grid over these telescopes and then just associate location in the beam with how bright the telescope measured the signal. So this is the beam as measured from the drone for 4 of the telescopes, both polarizations. You can pick out main beam features and side lobes. A polarization result was actually one of the key results from this paper, but these are a interesting future direction for being able to map beams for these smaller 6-meter style dishes, where the far field of these dishes is accessible. These measurements were some of the most precise measurements of both polarization and just amplitude of this beam ever made by a drone. It also allowed us to compare the different dishes to both simulations and amongst each other. One of the highlights of the future arrays that people are building in 21 centimeter for future 21 centimeter radio telescopes really rely on having identical dishes. And so being able to compare one dish to the other and check how well the fabrication, how closely each dish actually matches the desired pattern is key. And being able to make sure those dishes are very redundant is very important for these next generation of round dishes. We did also measure CHIME. This was more of an engineering run just to see if we could measure a signal from a drone from CHIME. It's complicated for a variety of reasons, but this was written up by Will, one of my graduate students. So he was also asked to make a GIF for this, which I then got to steal for this talk. So what's happening is the drone is moving from east to west in a slice across CHIME. It's rotating on one side, so we're mapping out one polarization as the drone goes one way, then it rotates 90 degrees and we measure the orthogonal polarization going back the other way. This is the actual CHIME data from that trajectory. So this is, slice from east to west, and then this is along the frequency direction. So again, we map out one frequency one polarization as we head in one direction, and then turn around and map out the other polarization in the other direction. So there are a lot of features that are, I'm gonna try to stop it at the right moment, see what happens. So there are a lot of interesting features that you can pick out. Nope, didn't work. Oh well. There are a lot of interesting features you could pick out from that GIF. There's a bunch of frequency-dependent structure in the beam shape, and then the side lobes were even visible from the drone. So it was a very successful engineering run, and we are looking forward to making more measurements of CHIME in the near future. So hopefully over the course of this talk, I've convinced you that there are new things and old things in radio astronomy. So for example, we have new results from CHIME, so the detection of cosmological 21 centimeter signal just from CHIME data alone. Holography is a new way to use an old radio technique. Holography has been around for a long time, but has never been used to actually measure the beams of telescopes. We have old problems. We always have to calibrate our instruments and their beams, but also new techniques through drones. We have 2 papers out from that. Our future work, of course, is moving towards dark energy with CHIME. So we are looking at how to relax that filtering and integrating the holography beams into the new data sets as we head towards BAO detection. Finally, many new experiments are coming online. HIRAX, which is a set of 6-meter dishes in South Africa, and CHORD, which is a set of 6-meter round dishes near CHIME, are coming online in the next year or 2. These are more amenable to these drone-based beam measurements because the far field is accessible by a drone, and so we're building up programs for measuring the beam shapes of these telescopes. As well, some of their key science goals are also baryon acoustic oscillations and dark energy. So we have kind of both new and old presented in 21 centimeter community. Thank you.
Maybe we'll start with Zoom to see if there are questions. You're getting applause from Zoom as well. Any questions on Zoom?
can I ask you, I think it was for experimentally, but still I didn't understand. So this is a difference between the two data for solar, with minimal and maximum. And you got something about the leakage of polarization.
Yeah.
I,
Yep. Yeah, I can go through it. Yeah, sure. So what's happening here is, so I'll start with just the holography data. So Y here means that we've measured the Y, we've measured one polarization of the CHIME antenna and the same polarization with the 26 meter, so they're aligned. Okay. Similarly, same with XX, so just the orthogonal version of that. So what's happening in the holography data is that we're finding that when we have an excellent polarization calibrator, such as the 26 meter, the XX polarization measurement still looks like a regular main beam shape, whereas the solar data is just CHIME alone, so it can only pick up the power from CHIME in one particular polarization. So in this case, as the sun goes overhead, you measure a double bump feature because the squared power that lives in this solar trajectory includes both the copolarization power and additional cross-polarization power. In this case, the cross-polarization power is so bright that the cross-pole beam is the brightest thing that you're seeing. So what you're actually seeing in this solar data is simply, let me go back, it's literally that this part doesn't matter, and you're only measuring this very significant cross-pole pattern. But you don't know that it's cross-pole. You can only, all you know is that you measured power and it has a double bump feature in it. You can't detect that it's coming from an additional cross-pole. So that was apparent only because when you take the holography data, which is a polarization calibrator, so you measure the combination of the copole and the cross-pole, you note that the cross-pole is very big, and so when you add them together, the residual signal is just coming from a cross-pole pattern. So to try to say that again, CHIME alone doesn't know that this is coming from cross-pole. All it measures is power, and it wouldn't know that it's coming from the fact that there's a lot of cross-pole signal in this particular polarization at this location and this frequency.
But CHIME is sensitive to polarization. CHIME can determine polarization of this.
Yeah, it can measure its cross-pole, but it doesn't know its level. So we don't have a way to calibrate the relative level of that cross-pole signal compared to the copole. Yeah, that requires something like holography, where we know the relative levels.
So visual antenna, you can basically map out the polarization diagram, as far as I remember from Yale. So you know which directions of the field.
Yeah, exactly.
So here you cannot, or so you don't know the diagram, or the diagram.
Yeah, that's right. We don't. Okay, so in order to actually calibrate the polarization response of a telescope, typically you need a polarized calibrator. So usually you would need something that's, for example, ideally a celestial source that's emitting a polarization signal. Yes, very good point. Yes. So for CHIME, the far field of CHIME's dish is very far. It's many kilometers, so we couldn't access it with the drone. But yes, no, thank you for bringing this up, because I don't know where it may or may not be one of the nearby slides. It's probably not. One of the key results from our CHIME, there we go. One of the key results from our drone measurements at Green Bank was actually a polarization measurement. So sorry to the people who don't care about polarization calibration of radio telescopes. But yes, the drone is a perfectly polarized source. So we never get that in radio astronomy. There are no celestial sources that are perfectly polarized. So the drone is really amazing this way. So what we did was take the drone, which emits only one linear polarization, and rotate it around in 360 degrees around. And then we watched the different polarizations of these feeds, these two different polarizations of a telescope change. And what you expect as you rotate around, of course, is that in one polarization you get a maximum, and at that same angle, in the orthogonal polarization, you have a minimum. So you expect that if I'm looking at the two different linear polarizations, where I have a maximum in one, I get a minimum in the other, and that it is, ideally starts at 0, and you get 2 rotations as you rotate this drone around. So that is what we found at low frequencies for two different types of feeds that were on these dishes. So I'll call them Hyrax and CHIME inputs. So those are 2 different types of feeds that were radio feeds that are on these dishes. And at low frequencies, you can see that that's largely true. These different lines are just different places in the beam because you don't know exactly where the center of the beam is when you're doing this rotation. And for both the Hyrax inputs and even if you squint, also true for the CHIME inputs, that's true at these low frequencies. At higher frequencies, that was absolutely not true. So CHIME was still well behaved and had that behavior that we expect. Hyrax did not. So this is the equivalent, just it's the same rotations, just at a different frequency. And the polarizations are starting to move into each other. They're no longer orthogonal with each other. And this was traced to a design flaw in the design of the Hyrax feeds. So this is actually the first example of a drone measurement feeding back to an instrument design. So this was one of our more fun results actually from this paper and really influenced the Hyrax antenna design. So we have new antennas as a result of doing these measurements. Sorry, yeah.
What additional insights we get about the dark energy when we combine these 21 centimeter with CMB data? Do we learn anything additional?
When we combine the BAO feature sizes with the CMB?
Yeah.
Yes, definitely, yeah. So I mean, at this, certainly at this point it's standard in cosmology to always combine CMB data sets with BAO. The CMB sets the size of the BAO feature size back at 400,000 years after the Big Bang. It also can calibrate this amount of matter in the universe, which is one of the inputs to comparing the BAO feature size with the CMB data. So yes, in practice, you combine every cosmological data set that you can get to do a joint fit between CMB, BAO, and supernova, et cetera. Yeah. Oh yeah.
Yeah, thanks very much, Laura. Very interesting. All of this talk of calibration made me think of something else which I don't know the answer to, so I'm asking you. There are a number of 21 centimeter experiments that are looking for the structure of neutral hydrogen higher redshift in the event of reionization. Do you have, I mean, obviously you have different science goals and different technical requirements, but do you have any crosstalk or do you learn anything from how they're coping with these foregrounds?
Yeah, definitely. We have different approaches, but I would say the field is starting to come together. They're a whole decade ahead, right? So they've been doing this for longer than we have. 21 centimeter cosmology started with trying to measure neutral hydrogen right after the CMB was formed. So we have used some of their foreground filtering in our CHIME analysis. And I would say we're starting to come to a consensus on how to build instruments that can do these measurements. We do all have the same problems. We're dealing with the same foregrounds. So a lot of the analysis techniques that they have really developed over the many years, we took advantage of for CHIME for sure. I think the next experiments that we're building in 21 centimeter low redshift for BAO are round dish-based experiments, and I don't think it's an accident that that is exactly what Hera, their kind of current generation epoch of reionization experiment is. So I think we're like coming to a consensus on what is the best instrument to actually build, to be able to both calibrate your beams and the other things in the instrument you need to calibrate. I think we're also starting to come to a consensus on what's important. So in HERA, this high redshift experiment that's ongoing right now, one of their signature problems is crosstalk between their different feeds. So they have these big round dishes and feeds that sit way above them, and the feeds can all talk to each other, and that's causing a lot of problems in their analysis right now. CHIME didn't do that, so if you look at our CHIME design, there's like a cylinder, and our feeds live right down far into the dish, and that's to shield them from seeing the other dishes. So I think, you know, there's kind of lessons learned on different sides, and I do think we're starting to come together on a design path for these kind of, how do you really build a 21 centimeter experiment?
Sorry, and just a follow-up, so that they're obviously operating at much lower frequencies, so can you use your synchrotron spectrum and use their data?
Like combined data. Right now, no. It's possible with HIREX we could. So just to say, CHIME is in the northern hemisphere, and we don't have any sky overlap because they have these dishes that just stare up at the sky. They can measure, and they really don't move at all. They can measure a small stripe of the sky, and unfortunately, there's no overlap. That will not necessarily be true with HIREX. So that's this future South African experiment, which is like basically right next to where HERA is. So there may be some way that we can trade data off there. And there is MWA, which is another one of these epoch of reionization experiments, has really beautiful maps of the southern sky. They're a more classic radio interferometer, so they're interested in making maps and measuring structures. And so they have some of the best low frequency maps at this point also. So yeah, I think we certainly hope to leverage that.
All right, one more question, Peter.
Okay. So in terms of cosmology, I'm wondering your prediction, how long it's going to take CHIME.
Oh, CHIME to do this? Yeah.
And maybe the next step on fifth around the CPU.
Yeah. So the next planned step, and of course these things can always go sideways, but the next planned step is to target the third peak of the BAO acoustic spectrum. So if you think in power spectrum space, that ring-like feature actually turns into harmonics. So the third bump, basically the third harmonic of that BAO feature size, is accessible at our lower frequency bands and a mild shifting of our current filtering. So I think we're aiming to measure the third peak. That's kind of where we think we're going to go next. Probably first in cross correlation with galaxy surveys. So I think we hope that that's not long now that we've demonstrated how to we've kind of gone through our power spectrum code and understand our data pretty well. So we're hoping that doesn't take very long, but it may. So I suspect that that will not necessarily change anything about lambda CDM in the near future, right? I think DESI is still DESI will be a better measurement of BAO for a while, and it will take longer for 21 centimeter to catch up with it as we work slowly through these analysis challenges. I think that's par for the course for cosmology. We do tend to, it can take a while when you have a new technique to kind of get up to the point where it becomes competitive with current measurements. Yeah.
All right, let's thank Laura again.